Hi everyone, welcome to the General Chemistry 1 lab. In this video we're going to go over the steps that you're going to do in Experiment 1. And Experiment 1 starts with an exercise where you're going to determine the density of a metal. In this course, when we determine the density of the metal, basically what you're going to do is, at the end of that, show the value to your TA. If you're close to the accepted density of that metal, you'll just proceed on to the next step. If there's some kind of mathematical calculation error or measuring error, you might have to redo a step, and then you will just move on to the next step after that. So this is essentially to give us practice with two things. The two things we're trying to practice here is making measurements, is one of the things we want to practice. And the other thing is doing calculations and reporting our answer with the correct number of significant figures. So it's really important that you're using the correct number of significant figures when you do this measurement. When you start, the first thing you're going to do is measure the mass of the metal. This will involve taking a small beaker, like the one Jesse is showing now, which has some metal in it, but you'll start with the small beaker being empty. You will then tare that on the balance. Tearing simply means zero it out. You're then going to add between 18 and 22 grams of your metal into the beaker. As you can see here, Jesse has already added the metal to the beaker. And in his case, he added 18.6943 grams of metal into the beaker. Note that the balance gives us 4 decimal places. Okay, we bought 4 decimal place balances. We need to record all 4 of those decimal places. Even if all of these were 18.0000, we would want to write down all of the zeros. Said another way, anytime you measure mass, make sure that you have 4 decimal places and make sure that you write all of those decimal places down. I'm now going to turn it over to Jesse, who's going to show you how to make the volume measurement using the graduated cylinder.
Hi everyone. So like Colin said, we're going to use a graduated cylinder to measure the volume of our water and our metal. First, notice that you have these large lines with numbers. Each of these goes up by 5, and these measure the volume in milliliters. In between, you'll notice that there are 10 lines between each of these, marking each one of these as half a milliliter. So this would be 20, 20 and a half, 21, 21 and a half, 22, and so on. It is important that you make use of these markings when measuring volume. So I'm going to measure 15 milliliters in this graduated cylinder. Now you could take a pipette like this and spend the next 3 hours dripping it in. Please don't do that. Instead, pour until you are fairly close. You then need to get down to about eye level, which I am doing behind the camera. Then you take your pipette and you carefully drip until that water is resting on the line. So now that we've moved the camera in a bit, if you'll note, when I tap this, you see this little surface of water here. It is curved. That's called a meniscus. You read the volume from the very bottom of this meniscus. Now there are different schools of thought on how to read this. You could read this as 15.0, which is what we're going to do for the purposes of this experiment. A more stringent or a more precise device might be read as 15.00. So now that I've got my reading of 15.0 milliliters, I'm going to add my metal. I have it zoomed in because it's not going to change a whole lot. So I'm going to give this a little tap, chase off the air bubble, and if I get down to eye level with my meniscus, you'll notice it is now reading 17.1 milliliters. So how did I get that at 17.1? Well, you see how we have the 15 and the water's here. So we go 15 and a half, 16, 16 and a half, 17, and we're just a bit above the 17. So that's why I'm calling it 17.1, because I can estimate that 0.1 in between the 17 and the 17 and a half. So the reason it went up is because we added the copper metal that displaced the water with its own volume. So the volume of the metal is the difference between the current volume and the volume in it was just water. Now that we have our measurements, I'm going to send it back to Colin, who's going to discuss the math.
So now that Jesse's made all of the measurements, the mass, again to 4 decimal places, and the volumes to 1 decimal place each, all we're left to do is to calculate the density of the metal. Note that's what's important here is your significant figures. So to find the volume of the metal, we need to take the final volume after the metal was added and subtract out the initial volume of the water. Because again, as Jesse said, we found the volume of the metal by displacement. So what we do is we take 17.1 milliliters and we subtract out our 15.0 milliliters. Note that in subtraction, we want the answer to have the same number of decimal places as the measurement with the least decimal places. In this case, both of our measurements have 1 decimal place because we measured them with the same device. It's very common that when you measure things with the same device, you have the same number of sig figs or the same number of decimal places. In this case, we get 2.1 milliliters, and fortunately, our calculator will actually give us the correct number of significant figures. So we can put that here as our volume. Now we need to find the density of the metal. In order to find the density of the metal, we need to use the formula. Density equals mass divided by volume. Well, we have the mass, which is 18.6943 grams, and we have the volume, which is 2.1 milliliters. When you do this and you plunge it into your calculator gives you a very, very long number. In this case, 8.902, so on and so forth. But what we need to do is we need to look at our values in order to get the correct number of significant figures. In this case, we're dividing. So when you're dividing or multiplying, you want to go with the least number of total sig figs. So if we go here, we have 1, 2, 3, 4, 5, 6 significant figures. And down here, we only have 2 significant figures. So we want to report our answer to 2 significant figures, which is 8.9 grams per milliliter. We would then report this value to our teaching assistant, who would let us know whether we're close to the accepted value. If you're not close for whatever reason, you may have to remeasure a volume or remeasure or recalculate something or whatever the case may be. After you have your value close to the accepted value, you can continue to the next step of the experiment. One common source of an error in an experiment like this is air bubbles, and this especially happens with plastic graduated cylinders. So if you're experiencing some air bubbles in your graduated cylinder, a good thing you could do is just gently knock it onto the countertop, and that will dislodge any air bubbles. Note that air has a very low density and will certainly have a much lower density than your metal. So having air bubbles can throw off your experimental results. Do what you can to minimize the air bubbles in your system.